Okay, this is Unit 9, Video 3, and this is Physics of Music. We're going to talk about instruments. We're going to talk about resonant frequencies on string and wind instruments. We're going to solve for the length of strings and pipes for musical instruments. Okay, so kind of a cool lecture today. All right, all objects have a resonant frequency. This is what we talked about when we said that all objects have like a natural frequency that they like to vibrate in. Okay, and that's usually what instruments use to make nice, pretty sounds. This is the frequency with which an object will oscillate naturally. In structures like bridges and buildings, this frequency is very low and best described as a slow sway. So like when we have earthquakes and you see buildings sort of like waving back and forth, those are their resonant frequencies. In musical instruments, the resonant frequency is usually between 300 and 3000 hertz. Remember, hertz is frequency, and 300 would be very low pitch. Low frequency is low pitch. 3000 would be a high pitch. Okay. Some examples would be like of resonance. Again, would be the student on a swing or a kid on a swing. The bridge video I showed you guys where the wind knocked that bridge down from just like swaying in the natural vibration of the bridge. Tall buildings during earthquakes. A prayer bowl. By hitting it, we sort of get it into its natural frequency. Sound waves are a result of physical vibrations. Okay, physical vibrations. So in order to have sound, we need vibration. So you're not going to do this with an elbow partner because you don't have one. So instead, we're just going to go through this together. So identify the physical vibration in a guitar. In a guitar, the thing that vibrates is a string, right? In a tuning fork, that's the thing that looks sort of like this. It's a little piece of metal, and you hit it with something else, and it sort of vibrates in the air, okay? And so the air and the metal tuning fork are what vibrate and cause a sound. A clarinet is going to be the air inside. When you talk, it's your vocal cords that vibrate, and then they actually vibrate the air around them, okay? Now, a harmonic is a property of a sound. And we say that the lowest frequency produced by any particular instrument is known as the fundamental frequency. Okay? We also call that the first harmonic. So the first harmonic and the fundamental frequency are the same thing. Okay? It's one of many harmonics. So instruments will vibrate at natural frequencies, but they can actually vibrate at different harmonics. Okay, so we'll talk about what I mean by that in a little bit. I'll kind of show you. But I'm going to draw these harmonics for a string. An open tube, which would mean that it would be a tube that's open at both ends. Okay, and then a closed tube would be a tube that's closed at one end. All right, if you have a tube that's closed at two ends, the air can't vibrate, right? We can't hear anything. So it's only closed at one end. Okay. So we're going to go ahead and draw the first harmonics, and then I'm hoping that I have this demo. I have this one demo that I'd really like to show you that you'll be able to see these waves and these harmonics. But for now, we're just gonna draw them, and then we'll talk about it in class. And if I have the demo, I will show it to you in class. Okay? Kind of hard to draw, so just stick with me here. I'm going to do my best. Okay, first harmonic looks like this. First string. So first harmonic. Okay, you'll notice it's half of a wavelength, right? If this wave were to continue, it would go like that, right? Something like that. I don't want to get in the way of this open pipe, but it's half of a wavelength, okay? Second harmonic, okay, would be a full wavelength. The reason I'm drawing like one on top of the other one is that when they're vibrating, they actually create this look, even though it's only one string. Okay, and I'll show you that on the demo, but that's what they look like. Third harmonic would be 1.5 wavelengths. So something like that. Okay, and the fourth harmonic would be 2 wavelengths. Okay, so do your best to draw those. Okay, two wavelengths. Remember, one wavelength is like that. Okay, and then this one has another half. Couple things to note about these things. The spots where the waves stand still are called nodes. So if we were to watch this vibrate, these parts of the wave would actually not be moving. Okay, and so those are called nodes. All right, and then where the amplitude is the highest, those are called antinodes. Okay. So the first harmonic has two nodes and one antinode. This second harmonic has three nodes and two antinodes. This third harmonic has 1, 2, 3, 4 nodes and 3 antinodes, and then 1, 2, 3, 4, 5 nodes and 4 antinodes. Okay? In an open tube, it will look like this. Okay? These sides won't be nodes because these are open tubes. Okay? And so the wave will sit in the air like this, and they won't actually have nodes at the ends here. Okay? Again, this would be a wavelength and a half. Okay. Third harmonic would be, oops, so that's one wavelength and a half. Sorry, and then this one's going to be 2 wavelengths here, so it's actually a little bit different in the open tube. Make sure I'm doing this right. Mess you guys up. Oops, I think that's like that. And then the last one looks like that. Okay? It's hard for me to draw them all the same size here. All right, and then a closed tube is going to look a little different. They're going to have where the side that's closed is going to have a node, and the other side will be open. Okay? So this first one, I'm actually going to draw it so that the open side is on this side. I don't know why that's easier for me. Okay, so this side's the closed end, so first one looks like that. Second one like that. Third harmonic like that. And then fourth harmonic like that. Okay? So just do your best to draw those. It is a little bit difficult, but draw those on there. Okay? And then there's an equation. So if we want to know the frequency of the first harmonic of any instrument, for string instruments, we would use this equation. So this is the frequency, okay? N is the number. So like F1 would be the fundamental frequency. F2 would be the second harmonic, okay? So this would be N, speed, and then 2L. L is the length of the string, okay? For an open pipe, okay, it's the same equation, where L is the length of the pipe, okay? And then a closed pipe is just a little bit different of an equation because a closed pipe only has odd numbered frequencies. So it has the first harmonic, the third, so F1, 3, 5, 7, 9. It can't have the in-between because of the way that the wave fits inside the tube with the closed end, okay, and having to have one node and then not a node, okay? So I want a couple notes here. So the units would be hertz because that's the frequency, okay? And then N is the harmonic number. V is the speed, okay? And then speed of the wave, right? And then L is the length, okay? And I'm actually going to add an example problem down here. So we're going to write out the example, and that way you can see it. Because this note set didn't have one, and I want us to do an example. So I'm going to add an example down here. So add this to your notes. Okay? So I'm going to say find the second harmonic of a 31 centimeter violin string, okay, if the waves on a string travel at 275 meters per second, and that's it, okay? All right, so let's write down what we know here. Okay, we want the second harmonic, so we're looking for Fn, or sorry, F2. Okay, we know N is 2. We know V is 275 because they told us the speed of the sound on a string. Okay, and then we know L is 31 centimeters, but we can't use centimeters, so we'll put 0.31 meters. Okay. Since it's on a string, we use this equation. Okay, so we have F2 equals 2 V, which is 275, over 2 times L, which is 0.31. Okay, and if you solve that, you get that F2 for this violin on that string, sorry, try to get out of the way here, is 887 hertz. So that's the frequency of the second harmonic of that violin string. Okay. Now, if you wanted the first harmonic, all that would happen is that this would stay the same, this would stay the same, this would change to 1. So basically this would just be divided by 2. So this would be 443.5. All right. The third harmonic would be this plus 443.5. The fourth harmonic would be this times 2, so times 2. So those are the natural frequencies of this string, okay, with that length and that speed. All right. They will sort of, okay. All right, let's move on. So turn to the back side, to this one. Now this is basically a separate lecture, but I combined them because neither one of them was very long, and I wanted to save us a day here. So in this part, we're going to actually talk about intensity, sound intensity, and loudness, which basically are the same thing. We're talking about the sound level, okay? And so the thing that I want you to remember is the Doppler effect's fine to remember, but I want you to really remember that frequency corresponds to pitch, okay? And amplitude corresponds to loudness. So when we're talking about sounds being louder, we're talking about the wave actually having a bigger amplitude, versus if it's a quieter sound, then the wave would have a smaller amplitude. Okay. Intensity is the rate at which energy flows through a unit area perpendicular to. Okay, so basically the rate at which energy flows through some area. Okay, that's intensity. So the more energy that flows through some specific amount of space, the higher the intensity, the louder that sound. Okay. The equation for intensity is power over surface area, and for us it's a circle, and so it's going to be 4 pi r squared. Okay, you can imagine sound going through this, like ring. Okay, and then let's see here. Hold on one second. Okay, sorry. So the units for intensity are watts per meter squared. Okay, so power is in watts, area is in meters squared. That's it. Okay, this is just going to be a plug and chug type of equation. All right. So let's just try one example, and then I'm going to get to the more fun, kind of interesting conceptual stuff. So what is the intensity of the sound waves produced by a trumpet at a distance of 3.2 meters? Okay, so obviously the closer you get to a sound, the louder it's going to feel, the more intense you're going to hear it. So the further you get away, the intensity of the sound actually decreases by a squared factor. So it actually gets quieter very quickly. So what is the intensity of sound waves produced by a trumpet at a distance of 3.2 meters? So that would be the R. And the reason we say that it's R is because you can imagine if you're a person here and there's a sound coming off some speaker or something. Okay, the sound is coming off in all directions. Okay, so R is 3.2. That's the distance, right, from here to the person. When the power output is 0.2 watts. All right, so you just plug in I is equal to 0.2 divided by 4 pi. R is 3.2 squared. And if you do the math, you get intensity equals 0.0016 watts per meter squared. Okay? So easy plug and chug, hopefully. Now, this is the more interesting part here. So I want to talk about this for a minute. All right. This chart here, okay, kind of hard to see on my video, but look at it on your paper. Okay. This is a graph of how humans hear. Okay, and so this side of the graph is frequency of sound, okay, and this side of the graph is intensity, okay, of the sound. So we actually hear best in this middle region, all right? This outer region, this says threshold of pain, this outer region is where it actually would hurt for us to hear sounds at that. So as you go up here, okay, you should see that you have more and more intensity. So the sound is much more loud and intense. And as you go this way, the frequency gets higher. So sounds that are in this region here, that's actually what we hear when we're speaking or when someone speaks to us. Okay, so an intensity of around 60 to 80 and a pitch of, somewhere between 100 or frequency 100 and about 5,000, okay, hertz. Right outside the speech is the music area, okay? And then outside of that is the area of sound we can hear, all right? And then this is actually the threshold of hearing, meaning this is when we can start hearing. So this line on the outside kind of tells you, like, here's where it would hurt, okay, is things up here, and then things down here, this is where anything below out here we probably can't hear. Now, some people hear better at higher pitches, some hear better at lower pitches, and so we're actually going to talk about that concept in class. Some people can hear, more down here. Some people can't even hear that part. As you get older, your ears get worse, and so you can't hear certain frequencies and things like that. But this is sort of a graph of how we hear, okay? Now, over here, we're talking about sound level in decibels, okay, and intensity. Now, these are just like sources of sound, just examples, okay? Now, when we measure sound level, okay, in decibels, the intensity actually is multiplied 10 times more intense for every 10 decibels that we go up. Now it's a logarithmic scale, so it's a little confusing to understand, but I want to kind of talk about this for a second. We're going to talk more in class because it's just kind of a hard concept and I want to be able to answer questions. But just so that you get the basic idea here, a jet plane at 30 meters is about 140 decibels, okay? And the intensity would be about 100, okay? Now, let's go like up 10. So let's go down here, okay? So the threshold of hearing, that's 0 decibels, all right? The intensity of 0 decibels is 1 times 10 to the negative 12. Now, a rustling of leaves is 10 decibels. 10 decibels is 10 times louder than, so the rustling of leaves is 10 times louder than 0, okay? A whisper is 10 times louder, more intense, than the rustle of leaves. Now here's where it gets kind of weird. If you think about this, as we'll do this example here, okay? I'm actually going to zoom back out here for a second. So at the bottom of your page here, okay? There are some facts here. So human hearing depends on both frequency and intensity of the sound waves. Sounds in the middle of the spectrum can be heard more easily. Loudness is related to the relative intensity of a sound wave. Relative intensity is measured in decibels because the human ear hears logarithmically. Okay, I'll explain what that means in a second. Sorry, try to focus this a little bit better here. The threshold of hearing is the softest sound that can be heard by a human. It depends on frequency and intensity. Okay. A decibel is a dimensionless unit that describes the ratio of two intensities of sound. So the threshold of hearing is the commonly used as the reference intensity. So that all sounds a little bit crazy. Let's just go through an example. The decibel level of an orchestra is 90 decibels. Okay. A single violin achieves a level of 70 decibels. How does the sound intensity from the full orchestra compare with that of the violin alone? Okay. For every 10 decibels you go up, the intensity is 10 times greater. So, how many decibels did we go up from a single violin to an orchestra? Should be very easy. We went up 20 decibels. How many times did we go up by 10, right? So we went up by 10 to 80, and then by 10 again. So the intensity from 70 to 80 would be 10 times greater. Okay? Decibels. From 70 to 90 is not 20 times greater. It's 10 times 10 times greater. Which means, so basically, for every 10 you go up, you do 10 to this exponent. So if we went up 10 twice, this would be 10 squared, which is actually 100 times greater. Okay? So it's kind of confusing, but if you think about it, you basically figure out the difference. Okay, their difference is 20 decibels. Okay, let me zoom out a little bit here. Okay, their difference is 20 decibels. 90 minus 70 is 20. Divide that by 10 and you get 2. That becomes the exponent on the 10 to figure out how many times greater the intensity would be. 10 squared is 100, so it's 100 times greater. Okay? We'll do more examples in class if you're a little bit confused. It's a little bit strange. Now, this one's even more confusing, in my opinion. So a noisy machine in a factory produces a decibel rating of 80 decibels. Okay? How many identical machines could be added to the factory without exceeding the 90 decibel limit set by the federal regulations? So if you have one machine that creates 80 decibels, by putting another machine that creates another 80 decibels, you are not making it 160 decibels. Okay? To go from 80 decibels to 90 decibels, you're going up 10 decibels, right? So 10 divided by 10 is 1, which means that 90 decibels is 10 to the 1 times more intense. So 10 times more intense. Okay? In order to make this room sound 10 times more intense, you would need to have 9 more machines. Okay? So 10 times more intense, so you can have actually 9 more machines like that to not break this. Now, if you had 10 more machines, then you'd have 11 machines total, and then you'd actually have 91, right? So that would not be good. But in order to get to 90, you already have 1 at 80. You could have 9 more machines at 80 decibels would make it 10 times more intense than having 1, because you'd have 10 instead of 1. Does that make sense? So the 9 is weird, but it's because you already have 1. And 90 is 10 times more than this. So you want to have 10 more. You basically want to have 10 machines, which is 10 times more than 1. It's kind of confusing. I'll explain more in class, but you could have 9 more machines and not exceed that limit. Okay? All right, that is it for this lesson. Let's go ahead and we'll talk more about these concepts in class.